Merci, Martin. Alors, comme Martin,
Thank you, Martin.
Je viens du département.
Thank you. I'm from the Department of Information Technology and Software Engineering. I feel like an imposter, and forestry is not my field of expertise. However, I must confess that you have very good problems, very nice problems. That's something that I'm attracted to. And so my research specialty is mobile robotics, but also automatic learning. So today, essentially, what I'm going to do is to present to you the expertise areas that we've developed at the DAMAS lab. This is a data analytics, mobile and autonomous systems. I'll show you the fields of expertise that I have developed. The two important lines of research that I consider as probably being important for forestry is the use of LiDAR and stereo cameras to do 3D mapping, and also navigation using mobile robots in unstructured environments such as forests. And I will give you a little course about automated machine learning very quickly to give you an idea of what we could do, what we can do with machine learning. If we look at 3D mapping, I would like to thank here Richard Fournier, who made a great introduction. The idea of putting LiDARs on mobile equipment. I will work on terrestrially. I'll take a terrestrial LiDAR that gives him a good data flow. I'll put that on a mobile robot, or we could put that in a backpack of a person walking, cruising the forest with an inertia sensor. The objective is to create 3D maps with special challenges that might be the equivalent of wanting to climb Mount Everest with your eyes blindfolded on one leg. We want to build all the equipment on our mobile robot with a LiDAR, an inertial device, and cameras. We also talk about space exploration. There's no GPS on Mars, so we do research where we consider that we don't have any GPS signals, and GPS is denied, and there's no astronauts that will put fiducial markers on Mars. So the important thing for us is to have a system which automatically will find natural reference points in the forest, branch points, trunks, and so on. So we have inertial surveying systems. If I don't have fiducial markers to do the registration spheres and class points in different point classes. Ideally, we would also like to be able to build maps in real time, but I leave that problem to Mr. Moore, who every 2 years, you know that computers increase their calculation speed. So it's just a matter of increasing the speed. What this can make possible for forestry, the capacity to have 3D maps on embarked onboard devices on vehicle, would be to extract standing street geometry on the fly when we do the harvesting, and as the machinery moves. If I've mounted a LiDAR on my vehicle, I can create these 3D maps on the fly and extract the geometry of the trees and get some data for my selective cutting. That could allow us to create quickly cheap 3D maps directly on the fly and have validation plots. Instead of doing it manually with LiDAR that we would move the vehicle, and quickly we could generate 3D maps. How do we solve those types of problems? We use a technique that is called SLAM, simultaneous localization and mapping. We have to put ourselves in the idea that we no longer have a GPS. How do I do my localization? I take a laser scan, I have my 3D map, and I will try to find out how to position my current scan on my 3D map. I use my map, I support myself on my map to do localization. How do we create a map? If I have the position for my scan, I will insert this in the map. You see, it's a problem of chicken and egg. I need a good map to do the localization, and I need to be very well localized to do the map. So it's not easy. It's a problem that will not necessarily converge. The quality of the map we get with the SLAM depends a lot on the trajectory that is followed, which is not a problem with LiDAR surveys. I have to give you an idea on how the SLAM works. You'll see a demonstration that was made by a research group at MIT, that what they used to take a 3D measurements. It's a Kinect. A Kinect gives us a color point cloud. You have red, blue, and green, and you have the distance for each of the pixels. Essentially, when we do SLAM, we try to solve some kind of a puzzle. The idea is as each scan is like one piece in the puzzle, it has a special shape, and when I move with my vehicle, I get a new piece of a puzzle. I try to put the different pieces of the puzzle together since I have a good 3D structure. The problem is that when you move like that, my pieces connect together, but I have error that accumulates because I don't have access to a GPS that gives me global referencing. So what we'll see in the video is how can we correct those errors that accumulate. You see here on the video at the beginning, the person moves with the Kinect, and this 3D map is built as the sensor moves. And eventually, the person decides to do a loop and turn in that building. It creates a kind of a square, and at the end, we have an error. You see that the map doesn't fit. There is a gap between the beginning and end, whereas it should be the same place. What is done with the SLAM, we just detect that there's supposed to be a loop closure, and then we deform that relatively flexible map to adjust the beginning and the end of the loop when we detected a loop closure. Same thing when we do puzzles at home. When we do the edges, we always start with the edges in a puzzle. At the end, if the pieces don't fit, you just move them, you pull them, and physically all the error is corrected back. So the SLAM allows us to create these maps without having any global referencing system about positioning. In our case, what we use, we have a robot at home. It's a Husky made by ClearPath. We have lasers on different units to have a 3D scan based on a 2D laser. We also have access to a Verodyne that has 32 lasers, so it scans 360 degrees, about 700,000 points per second. And we move the robot, and then at some intervals, we take a 360 scan. Each of those scans is one piece of the puzzle that I will try to assemble after that. This is a project that we started very recently. We don't yet have any concrete results. It's a project done in the Institute of Bioeconomics of Norway. I have a student called Marek, who is from Norway. I collaborate with him to be able to create those 3D maps. Here is an example. We used a software package that comes from the University of Sherbrooke. It's called ArgelMap. It allows us to create in real time these 3D maps. What you see here on this side are stereo images, colored 3D images. And you can see here how we can recreate, as the robot travels, we can recreate the environment in 3D as the robot moves. We can't do the loop closures. We still have a problem with closing the loops. It's a very difficult problem, as I said. But it gives you a good idea of what we can do with that. As a vehicle moves, I can create these 3D maps. What else can we do when we put a LiDAR on board a vehicle? As I said, I'm in mobile robotics, so I try to do travel and navigation automation. There is a technique which is relatively simple, which is the teach and repeat. One of the problems when we work in robotics, whether it be with robots in plants and industrial facilities or on the ground in the field, is how do we program our robots? We can take a specialized engineer who will type command lines in a script on a computer to choose a trajectory to move parts from one treadmill to another treadmill. But more and more, we try to have natural interfaces to be able to program the robot itself. In the plant, for example, what we can do is move the robot arm and move it to show the robot, here is what you should do. That's what we do also with the teach and repeat for robots. In the first phase, which is the teach, what do we do? I have my robot, my forest equipment, on which I put a LiDAR or an inertial surveying system on board, and I simply move the robot to the place where I want the robot to travel. It's just like if I'm putting a virtual dream in the robot. It's like a rail. It's putting a virtual rail. And now you have the possibility of automating transport operations. For example, once I've done this teaching with the robot, then it's like a virtual rail. I can displace any vehicle along that same virtual rail. That's the repeat part. What's in it for the forest industry? I think it allows us to create a kind of a virtual roadmap a virtual road network. I show it in blue here. So you have a person who doesn't know exactly how a robot works. The only thing the person has to do is to drive the vehicle, moving the sensors, and we'll take measurements. We'll take a 3D scan every meter, and we will also record the position of the vehicle on that small map. Here, I'm not trying to do a globally consistent map. I'm just doing a local map, and every meter I change the map, but I record the travel. What I can do with that is to have a whole series of other vehicles who will be able to follow the same trajectories on your network, creating a roadmap. Is that pipe dream? Is that impossible to do? Here you have research results from last year. I had David Landry, who was at the time an intern in computer science. That person had never touched a LiDAR in his life. He'd never touched a robot with an inertial surveying device. And here is what he was able to do within 8 weeks. In the video, you will see both the teach and the repeat phase. We put a fixed camera and we recorded the trajectory. We made a video that showed the trajectory during the teach. Then we asked the robot to do the repeat. And what we did, we superimposed both videos, one on top of another. So if you see only one robot, it means that the trajectory is good, it's perfect. Sometimes what you'll see in the video is that the robot is kind of duplicated. We have little travel errors, but overall, we did that also in the forest to have a navigable soil. We can reproduce up to a few centimeters at the same time the trajectory that had been taught at the beginning simply by moving the robot. Even if there is a slight sliding, the system recovers and corrects itself automatically.
And we can plant some spikes just to see what the error is. I challenge you to drive a vehicle and have an error of 1 centimeter. And what's special here is that this training was done by someone who's not a professional. So let's have a little course on machine learning. We've had several presentations today that did classification. What's machine learning? Well, it's not complicated. It starts, first we have a classifier with automatic functions or algorithms. And what do we feed it? Well, we feed it information. Here I have the picture of a cat. And then what comes out the other end is a name. So here the classifier recognized that it's a cat. So that's the machine part. Now the learning part is how do we create these classifiers? These classifiers don't come already in a box. No, we have to train them. How do we train the classifiers? What I need data, training data. So examples, so images of cat, and labels. Say the word cat. Why do I mention this? Because several people here have never done any machine learning. So if you have a problem and you can give us labeled information, say this is the species of wood and this is the kind of river, and you have enough information, all you have to do is give that to a data scientist, and he will work with the different algorithms. They'll be able to classify. So that's what the take-home message is. If you have labeled information, we'll be able to do something with the information. We've seen many presentations where people were explaining LiDAR data, multispectral LiDAR. But if you have labels, it helps the processing of the data. Visual object classification has been progressive in the past few years. The Google company had software with the DeepMind company that they bought afterwards. So this is a very complex problem, and we want to show the progress that's been made over the past few years in automated learning. So before the year 2000, we already had 50,000 images, a dog, a bike. We were able to put a box around an image, for example, a dog. So the system was able to recognize a dog. And then in 2012, we had a game changer in LiDAR. The game changer was ImageNet. When I talk about data, 14 million images with 1,000 different classes. With these numbers, we're able to have classifiers that are as effective as humans. So before we wanted to know what this was. It was a dog. Now I ask you, humans, what kind of dog is this? Can anyone tell me what kind of dog this is? People are wondering. So now these systems can tell you this is a West Island White Terrier. So this is the level that we're at right now. The database has 120 different types of dog. At Damas, what we're doing in machine learning, surface terrain ID from accelerator meter data, grasping point ID from RGB decolored 3D images, and image recognition using deep learning. Same thing that Google uses now, and that we can get similar kind of results. How can it be used in forestry? If you place boxes with accelerometers, we can classify, are these vibrations good, bad, or fair road conditions? The vehicle has to be able to come back to its point of departure, and then we can take out the data. We can detect slip, and we can detect when vehicles are getting stuck, and we can identify tree species and water courses. So the basic concept is that if you have labels for your data, we can make a classifier for it. So the take-home message here, 3D sensing and mapping have made immense progress in the last 10 years. Machine learning as well. Using both will lead to a greater autonomy, unparalleled autonomy. We can look at Buka and others. I think, sincerely, that the time is right. There are great advances in machine learning, and I think that we can really do something interesting when we're talking about 4.0 industrialization. This is where we're at. Thank you very much.